Hello, I'm Kenichiro Fukushi from NEC, Japan. In this video, I will introduce our recent work, Few-Shot Generative Model for Skeleton-based Human Action Synthesis using Cross-Domain Adversarial Learning. We propose the first few-shot generative models of human actions to the best of our knowledge. As depicted in the below picture, it is based on the Generative Adversarial Network GAN, and we introduced the novel cross-domain and entropy regularization losses from exploiting the variation within large public datasets. We confirmed improved recognition accuracy using data augmented by the proposed method. Here are some generated samples. Throughout our study, we deal with skeleton-based motion. 25 samples are visualized due to space limitation. Our method successfully synthesizes actions in different ways using only 10 training samples. The skeletal sequence represents both the diversity and plausibility. Let me show you the detail. First, our motivation is how can we synthesize diverse and plausible human actions from few-shot data. Collecting human action data is time-consuming and labor-intensive. Therefore, few-shot scenarios are often the case, but limited collection of data deteriorates deep models such as human action recognition (HAR). However, no effective augmentation method of human action has been established. Traditional geometric augmentation methods hardly synthesize plausible human actions. Existing generative models for human action synthesis are designed for scenarios that contain thousands of training motion samples, not few-shot. Diverse and plausible synthesis enables training deep models in few-shot scenarios by avoiding overfitting. Our approach is to exploit large public datasets as a source of motion variations. The proposed method extends one of the state-of-the-art models, kinetic GAN, by introducing novel regularization losses. First, we find reference motion from the source dataset at the patch level that is similar to target samples. Next, in adversarial training, we transfer the variation in the reference motion patches. Cross-domain regularization guides the generator to remain consistent with the reference motions. Entropy regularization encourages the generator to capture the distribution of the reference motions to enhance diversity. We define reference motion patches as a set of source motion patches from action class I that are similar to the target motion. First, the target dataset and each action in the source dataset are averaged. Next, each averaged sample are divided into patches with a sliding window of length k. The nearest neighbors within the source patch motion are then calculated using the cosine similarity. Finally, the reference motion patches for kth patch of target samples are extracted from the source dataset of action class I and patch position j that are same as the corresponding nearest neighbor. Cross-domain regularization encourages the generated samples to resemble the reference motion at the patch level. We formulate this as the distance of nearest neighbor reference motion patches from the generated motion. Given the generated samples from a batch of B noise vector, the loss function is expressed using the cosine similarity of the nearest neighbor reference motion patches. As the generated motion becomes closer to the reference motion at the patch level, the loss becomes smaller. This causes the generator to be guided by the source dataset. Entropy regularization encourages the generated samples to follow the distribution of the reference motion patches. We formulate this as the entropy of the distribution of nearest neighbor reference motion patches. As the generated samples have more number of different nearest neighbors, the loss becomes smaller. This is effective for avoiding mode collapse, where the generator falls into using a small subset of reference motion patches. We validate our method by applying it to data augmentation for action recognition tasks. We confirmed action recognition with the spatial temporal graph convolutional networks, so-called ST-GCN model, improves most when using the samples generated by the proposed method. As the source domain, we utilize NTU RGB+D, and as the target domain, we utilize 30 samples from 3 characteristic action classes in NTU 120 RGB+D: run on the spot, sidekick, and stretch oneself, which are not included in NTU RGB+D. We compare the classification accuracy using ST-GCN with and without augmentation. The state-of-the-art methods Kinetic GAN and ACTA are compared with our method. The results demonstrate that data augmented with the proposed method improve classification accuracy by 28%. We further investigate how the effectiveness of data augmentation changes with the number of real samples. As shown in the bottom figure, our method keeps high accuracy, which means the effect of data augmentation is prominent with few real samples. We also examine synthesis-oriented metrics, the diversity, and multimodality. We observed the highest multimodality for our method, which may have prevented overfitting of ST-GCN. Diversity is defined as the interclass variance of generated samples. Multimodality is defined as the intraclass variance of generated samples. I conclude this video with this slide. We presented a few-shot learning method for skeleton-based motion synthesis. Cross-domain and entropy regularization are proposed to transfer the diversity of the large dataset of the source domain to the target domain. Experimental results demonstrated that the generated samples could be used as augmented data to train action recognition models. Thank you for listening.